his country or his interests. He isn't just crunching numbers, he likes to see his visions carried out.
As soon as the idea was proposed, it was challenged by skeptics.
When Sheikh Mohammed came up with the palm, there were cynics. People said the palm couldn't be done because of the sheer size and the shape.
But it was necessary. The Sheikh's vision of a tourist Shangri-La required beaches. Dubai has 41 miles of natural beaches, but the building boom had swallowed up all of the available beachfront property.
However, Dubai is clever. They're not stopping on the ground. They are actually extending their land area out into the sea itself.
By creating 48 miles of additional beachfront, the Palm Jumeirah more than doubles the size of the entire Dubai coastline. Not surprisingly, Sheikh Mohammed has ordered up 2 more palms. Once completed, the twins will join the Palm Jumeirah as 3 of the rare man-made structures visible from space.
To build the Palm Island, it took 93 million cubic meters of sand. To build the second palm, it was 123 million cubic meters of sand. To build the third palm, it's above 800 million cubic meters.
And as part of a constant quest to push engineering and design boundaries, Sheikh Mohammed was presented with an even greater challenge.
The palms are a very beautiful projects, but they're not true island destinations. They're connected to the city by a bridge. We thought of a concept of building 300 man-made islands and shape it like the world.
So how do you build an island? Or in this case, a whole new world?
You have to take 3 factors into mind. First is protecting the island.
Protection requires a breakwater, a wall that separates the waves and the sea from the construction inside. For the world, 37 million tons of rock, forged from the Gulf, were used to complete its breakwater. Once in place, engineers are free to begin forming the island.
To build the island, you need sand, and you cannot use desert sand. You can only use marine sand, seabed sand.
Desert sand doesn't work because it is finer, while marine sand has been introduced into that underwater environment, and its denser, more jagged grains are not easily flushed away by the tide.
The sand has been under the water and it's used to the seabed. It's used to the water itself. So we use sand which has already been there. We're not introducing anything new.
While dredging is not a new technology, no one had even conceived of applying it on as grand a scale as Dubai. 2 different dredgers are used to get the job done. The first is a cutter section dredger.
It's a kind of an oil rig. The boat stays where it is. There's a drill that goes into the seabed and starts cutting into the seabed.
The dredgers slice up to 80 feet below the seafloor. As it cuts, it is dragged horizontally, and all loose material is dredged up and pumped through a floating pipeline to its target. The other method for collecting sand is the suction hopper dredger.
It acts like a vacuum machine which basically hoovers the ground and which stores the sand in its belly and come back and start reclaiming.
A pile of sand, no matter how big, does not make an island. In order to turn sand into solid ground, Dubai's engineers use a process called vibrocompaction. Weighing over 5,000 pounds, this giant drill penetrates 50 feet below the surface. Vibration, combined with water saturation, rearranges loose sand grains into a more compact state.
And it keeps on shaking the ground until the particle of sand comes together and comes closer, and it solidifies, it gets stronger. It does to the ground in 1 hour what it took Mother Nature 10,000 years. It's speeding up the process of creating Earth.
With up to 13 hopper dredgers working on a single site and the vibro compactors chugging away, islands are being constructed at a staggering rate.
When we started reclamation of the world, on average, an island would be born every week. And we have 300 islands.
Over 320 million cubic meters of sand, or over 259,000 acres, have been used to create all the islands of the world. With sand in seemingly limitless supply, there appears to be no sign of a construction slowdown.
We're always asked, what's the future? It's a very difficult challenge for us to come up with new projects that are as mind-boggling as the ones we have. So we have a project which is still in the planning phase. We have built the world, now we're going to build the universe.
Not to be outdone, architects have taken on an even greater challenge, harnessing two other forces of nature, the sun and wind, in the service of this impossible city. Here in Dubai, the sun and wind are often relentless and always the enemies of any structures that are built here. But in a city where top designers are called starchitects, they're even finding ways to tame the harshest forces of nature. In the case of the dynamic tower, the energy of the sun and wind is being harnessed and used to power the building. Impossible as it may sound, the tower will be the world's first building in motion. Set to be completed in 2012, each floor of this 80-story building will hang like a ring around a stationary cement core. The top 10 floors are penthouses, and those residents can control when they move, turning 360 degrees in as little as 90 minutes. The bottom 70 floors are programmed electronically to take advantage of solar energy. To maximize wind power, giant turbine blades will be inserted horizontally in between the floors of the building.
If I have an 80-story building like the one in Dubai, we can have 79 wind turbines, which means a power station.
Each floor rotating independently makes it possible for sun exposure on the roof's solar panels, allowing 100% of its energy to be self-generated.
It's about time, really, that buildings will be self-powered. So this is the solution.
As the sun beats down on this desert city, temperatures can reach 120 degrees, and only 5 inches of rain falls each year. Since the early days of settlement, residents of Dubai have used the harsh elements to their advantage. Take the wind towers that can be found along the Dubai Creek. Here, residents once cooled their homes by draping wet cloths on dowels within the towers.
And when the winds came in, the towers trapped the wind, cooled it through the wet cloth, and then it came down into the residences like some sort of natural air conditioning. The wind towers is an interesting aspect of the cultural heritage of Dubai. It is guided and developed from environmental traditions of the area because of the hot and humid weather.
In 2007, architect Jesse Reiser faced the same challenge with slightly higher stakes. His design? The O14. And where did Reiser go for inspiration for this iconic structure? To the area's Islamic architectural history.
That kind of decorative impulse was also a very functional one. It shaded the buildings from the heat and glare of the sun.
This type of Islamic screen or window is known as jali.
There's a renewed interest in bringing together structure and ornament in buildings. And that was very much a part of the traditional way of designing here.
With traditional skyscrapers, glass windows cover the outside of the building and the structural core is inside. But Dubai's desert environment forced designers and engineers to consider another approach. Their design could be a glimpse into the future of high-rise engineering.
But we inverted the process. We pulled all of that material to the outside of the building, and we gained tremendous benefits by doing so. The structure became the sunscreen.
The load-bearing structure of the O14 wall isn't hidden inside the building. It is instead an exoskeleton. The tubular shape makes O14 even more sturdy than traditional high-rises because stress spreads throughout the structure rather than concentrating in the corners. Creating the exoskeleton requires that construction workers painstakingly build the shell one entire floor at a time by pouring cement in between two steel plates. These temporary metal encasements hold in the building's steel reinforcement mesh and circular moldings, which workers eventually hammer out to form holes.
We use a very liquid concrete mix, which is poured from above, and it fills every single void and crevice.
The sand in O14's concrete is much finer than that found in conventional concrete mixture.
We couldn't use concrete that had too much heavy sand. It had to be a super liquid mix in order for the concrete to penetrate all of the intricate spaces that were developed between the holes.
An added benefit of O14's design is a 3-foot gap between the concrete exterior wall and interior glass. The gap creates a chimney effect where hot air enters through the 1,326 holes in the exterior, some of which are 3 stories high, and then rises up past the windows.
This narrow space creates a conduit for the warm air to rise, and the rush of air substantially cools the interior of the building.
The chimney effect, combined with the shade created by the exoskeleton, will reduce the building's cooling costs by 30%. By the time of its completion in spring of 2009, the 22-story O14 will likely be added to the growing list of this city's engineering icons. Dubai is building the world and rules the sky. But can this impossible city defy all laws of nature and bring snow to the desert? Never before in recorded history has snow ever fallen in Dubai. In fact, temperatures often soar past 100 degrees during its summer months. So in a desert town perched on a gulf as warm as a bathtub, what could be more exotic than ice? How about an entire bar made of ice?